Hello everyone. Welcome to Geeks for Geeks Practice. So today we are going to see a question that was recently asked in an interview at Adobe, and that question mainly deals with recursion. So let's have a look at it. So if you observe over here, the question says that we need to count possible paths from top left to bottom right. So I know that the description of question is quite brief, so let's try to understand it in detail. So in order to do this, let's go to the whiteboard and have a look at it. So over here, let's read it out. There is a task, and the task is that we need to count all the possible paths from top left to bottom right of a m cross n matrix. Okay. Now, as we know that there is a m cross n matrix, so let's try to go to the sample input and output in order to understand how this question could be understood in a better way. So let's say the value of m is 2, which is there in the sample input, and value of n is 2. Let's draw a matrix of 2 cross 2. I'm numbering it from 1. So this is my first row. This is my second row. This is my first column. And this is my second column. Okay. So what will be top left? Can I say this cell will be top left? And bottom right, this cell will be bottom right. So what we need to do finally, we need to count all the possible paths. We need to count all the possible paths from top left to bottom right. All right. So what could be the possible paths over here? Like either we can move like from here to here, from here to here, or diagonally, right? But see, this is what we need to learn over here. We have just read the first two lines of the question and we have come over here and we are just searching all the possible paths. Let's also have a look at what paths are allowed in the question. Okay, great. So it is saying with the constraints that from each cell, you can either move only to right or down. So can I say that this path, this diagonal will be eliminated and we will have only two possible paths. That is, it will go from 1 comma 1 to 1 comma 2. Then it will straight come to 2 comma 2. Okay, and if this has become too clumsy, let me draw another one. That is the first path. Okay, this is the first path. And the second path will be like this because we are allowed to move down and we are also allowed to move right. So hence the explanation is there are two possible ways in this particular 2 cross 2 grid. So I hope the question is clear to you. Now let's try to develop the logic for this question. How can we solve it? So let me take a fresh whiteboard for that. Okay, so I have just now explained the question with a 2 cross 2 grid, but in order to explain the logic, I'll take a bigger input, okay? So let's say the bigger input is a 3 cross 3 grid. Okay. Let me draw it. Let me number them. I have kept the indexing with 1. So these are my 3 rows and these are my 3 columns. All right. Now, as we have already seen that we need to reach from 1 comma 1 to 3 comma 3, right? That is my top left and this is my bottom right. All right. So what we can do is, let's take any cell. Okay, let's take this cell. Let's take this cell. Let's try to find out. Like what first thing that comes to my mind is what are the possible places from where we can come to 2 comma 2. Okay, so as far as I can observe, I'm only allowed to move either right or down, right? So if I am over here, then I can come down. If I'm over here, then I can go right. So can I say that these two places, if I add them, like the solutions for these two places, if I add them, that is the number of possible paths that I go from 1 comma 1 to 2 comma 2. Okay, but what's there in the question? In the question, it is given that we need to reach till 3 comma 3. So I'll apply the same logic over here. What I'll do is, let me take a fresh grid. What I'm saying is, if I need to reach over here, I will see what are the possible ways I can reach over here and what are the possible ways I can reach over here. Okay, like this cell is, if I do the numbering, this cell is 2, 3, right? And let me number all of them. Okay, and this cell is 3, 2. Okay, so I'll be adding the solutions of 2, 3 and 3, 2 because these are the only two possible paths with the help of these constants that are allowed for me in order to reach 3 comma 3. Okay, so how can we increase or let's say how can we utilize this logic to solve the question? I'm just trying to give you a feel of smaller sub problems over here, and let's see how it goes. So suppose now you know that to reach 3 comma 3 you need the answers for this and this, right? Similarly, in order to reach this 2 comma 3 you need the answer of 1 3 and 2 2, right? Because you are only allowed to move right and bottom, keeping in mind this constant. So if you take now this one, suppose you can reach to this 2 comma 2 only from either 1 comma 2 or 2 comma 1. So don't you think like this is just like we are trying to solve smaller sub problems, and at the end we are combining the logic to find our eventual answer? All right, so now what we can do is, let's try to think like where can we end in the sense how, for how long do we need to do this? Like if I suppose if I reach over here, right, then I don't have anything, right? See, this is out of my matrix. So how to tackle all the situations? So in order to understand that, let's take two smaller inputs. There will be one grid, let's say, which has only one column, okay, and the other smaller input is there will be one grid which has only one row. Okay, and this is allowed. This is allowed. Why this is allowed? Because if you go to the constant now, okay, if you go to the constant, see, my m and n, they can vary from greater than equal to 1, less than equals to 100, both of them, right? So I can take, yeah. So over here, I have three columns, one row, and over here I have three rows and one column. Okay, so I will try to answer this particular piece of query, like what will happen over here when we are like at 1 comma 1, what will be the scenario with the help of these two smaller inputs. But in order to appreciate this, in order to appreciate the usefulness of these two smaller inputs, let me first write a very small recursive solution for this question. Okay, so let me just make this portion clear a bit. Very sorry. Yeah. Yeah. So let's say I am solving a grid of m comma n, where m is my rows and n is my columns. So the answer for this will be calculated from solve m minus 1 comma n. Don't worry, I'll explain this. Plus solve m comma n minus 1. I hope the board is visible to you. Yeah. So what is this solve m minus 1 comma n? If you carefully observe, we have m as row, n as column. So this is one row less than your previous one, but in the same column, right? So one row less than your previous one. Like let's say you are over here. This is your mn, okay? So m minus 1 is basically this place, right? This row. This is your m minus 1 row, and your n is the same column. So I'm referring to this particular position, right? M minus 1 comma n. Similarly, over here, if we have m comma n minus 1, it means we are in the same row, but we are one column before that. So I'm referring to this position. This is what I just explained, right? In order to calculate the answer for 3 comma 3, I'm taking help of 2 comma 3 and 3 comma 2, and that's what I have written over here. If I take mn at this position, this is my m minus 1 comma n, and this is my m comma n minus 1, and that's what I'm doing over here. But where should I stop? Right, you over here, if you reach what you are seeing is you cannot go outside your grid. Okay, so for that, there is a concept of base case in recursion. You need to write your base case because you cannot go infinite time calling your same function again and again. Right. So in order to understand that, let's have a look at these two inputs. So if you carefully observe, this is, let's say I have these three positions. Okay, this one, and this one. What are the possible ways to reach from here to here? Can I say only one? Because you are allowed only to move right and down. So there is no right cell over here. So I'll move only down, right? And what is the number of possible ways to reach from here to here? Right, from first cell to last cell. Can I say it's only one? Because you are allowed to move only right. And obviously there is no path that will go down, right? So this will serve as our base case. Like what we'll do, let me clear this area a bit. Okay, it has become let me try to zoom this out. Okay, yeah, so what I'm saying is, if, just a second, if my m equals 1, okay, or my n equals 1, any one of them, then what I need to do, I can simply return 1, because there is only one possible path. I can simply return 1. Okay, so we have our recursion formula, we have our base case, right? Now let's try to understand it in a different manner. Different manner in the sense, can I improvise the solution, or can I make it better? What if I get repetitive sub problems? Then what we need to do? Okay, so in order to appreciate that concept, we need to draw the recursion tree. Okay, so I'll clear the screen for a moment and I'll draw the recursion tree, or we can take a fresh whiteboard, not a problem. So yeah, so I am talking about 3 comma 3. Okay, let me draw this matrix 3 comma 3 over here. Okay, yeah, I need to reach over here from here. This board is okay. Yeah, fine. I'm really sorry for the interruption. So let's proceed. So we are going to reach from here to here, right? And we have already seen that in order to reach over here, we need to add the solutions of these two places, right? So let me number them. This is 1, 2, and 3. And over here, this is also 1, 2, and 3. Now, in order to understand it in a better way, let me write the recursive formula also that we were using. So it was solve m comma n equals to, basically I'll be utilizing this space to draw my recursion tree, equals to solve m minus 1 comma n plus solve m comma n minus 1. And what was our base case? If m is equals to 1 or n is equals to 1, we were returning, right? We were returning 1. All right. Now what will happen with 3 comma 3? My m is 3 and my n is 3, right? So m minus 1 is 2, n is 3. So this will call to the sub problem 2 comma 3. And this will become 3, that is m, and this will become n minus 1, that is 2. Now I have not written it just like that blindly. Okay, I have use this particular formula. Mn is 3, 3. So m minus 1 comma n is 2, 3. M comma n minus 1 is 3, 2. In order to cross verify it once again, you can also cross verify it from here. See, this is your 2, 3, right? And this is your 3, 2. And that's what I've written over here. Now, if I go further, what will happen? This is m minus 1 comma n. So this will become 1, 3. This will become m comma n minus 1. So this will become 2, 2. Let's cross verify this as well. What is your 2, 3? Your 2, 3 is this place, right? So what are the two sub problems you need? You need 1, 3 and you need 2, 2. And that's what we have got. After this will again become m minus 1 comma n. So 2, 2. And this will become m comma n minus 1. So this will become 3, 1, right? So let's check this also. 3, 2 is your this cell, right? So you have 2, 2 over here because you can come down and you have your final answer. And you have 3, 1 also because you can go right and you have your answer. So there's a very interesting catch over here in the recursive tree right now. I am saying that I am calculating this sub problem 2 comma 2 two times. I think I can improvise this. And this is this is the place where dynamic programming comes into picture. It is recursion plus whatever multiple or similar problems you are trying to evaluate. You don't need to evaluate it again and again. What you can do, you can create a storage, and over there you can store it. For example, I can store 2 comma 2 one time, or rather for the first time, and at later point of time I'll not again calculate 2 comma 2. Why am I saying this? Because see, if you proceed further, this will again become m minus 1 comma n, right? So this will be 1, 2, and this will become m comma n minus 1, right? So this will become 2, 1. And you can cross verify, like if you are here over 2, 2, so 1, 2 is basically this place, right? And 2, 1 is your this place, right? So, oh, really sorry. Yeah, so 1, 2 is your this place and 2, 1 is your this position. So again, like if you do the recursive tree, if you draw it further, you will again have those two similar calls. So why to call so many times? Like it's not required, right? So we'll try to improvise our solution. What we'll do, we'll take a two-dimensional array, okay? And I'll talk about the size of the array in just a moment. But I hope till now everything is clear to you. Like what is happening? Like we have the recursive tree, we have similar subproblems. It's not required that we calculate the same problem again and again. Like now it's fine, but what if this m and n is, let's say, 90 and n is 100? Then you will have a large number of same subproblems calculated again and again, right? And in competitive contests, you could get time limit exceeded for this. So there you need to be smart, right? You need to use some extra space so that you can store your initial solution for the very first time, and at later point of time you can cross check that, okay, whether I have the solution already calculated or not. If it is already calculated, then you don't need to calculate it again, right? So let's see how can we store this. Okay, let's see how can we store this. So I'll erase this part of the screen. Okay. Yeah, so what are the two things over here? M and n, right? These are m and n. Everywhere these are m and n, right? The values which are changing all are m and n. What could be my range of m and n? If you carefully observe, initially my range was greater than equals to 1 and less than equals to 100, right? Like if I go back to the question once again, the constants, see, it's between 1 and 100, right? Like inclusive of 1 and 100. So let me go to the whiteboard. Similarly for n. So if I take a DP array, let's say I take a DP array that is two-dimensional in nature, okay? In worst, what could be the possible subproblem? Can I say the possible worst subproblem could be 100, 100, like m will also become 100 and n will also become 100, right? And as we all know that the indexing is from 0, so the size that we need to take is 101, 101. Just to clarify, let's say this is your array, okay? and this goes from 0, 1, 2, 3. This is your indexing, right? This is your indexing. Now I am calculating, let's say for the last position. Okay, let's say I'm calculating for this position, right? So this is, see, indexing is one less than the position. Like this is my first position, this is my second position, third position, fourth position, right? So indexing is one less than my position. And in order to avoid confusion, I'm just taking one greater than my maximum value so that I can exactly say that, okay, fine, at DP 100, 100, I have my answer. What do I mean to say is if I extend this, okay, and if I extend this like this, okay, so let's say we have 101 rows and 101 columns. So it will go till 0 till 100, right? Over here also, this will go from 0 till 100. Right? So over here, I can straight away say that, okay, at 100, 100, I have my answer, right? So I hope this is clear to you, like what should be the size of our DP array and why are we taking DP array in order to store all the smaller subproblem answers. Okay, so if everything is clear at till this point of time, what we can do is we need to understand how we are keeping a track of already calculated some smaller subproblem. Okay, so what we'll do for that is we'll initialize all the positions. Okay, all the positions of our DP array. I know the diagram is not properly clear, but okay, or let me draw it fresh. Let me erase it. Yeah. Okay, this goes from 0 till 100. Okay, over here also this goes from 0 till 100. So what I'll do, as I am, these are all my columns, okay, and these are all my rows. So what I will do over here, I will initialize all the cells of my DP two-dimensional array with -1. Okay, why -1? Because it will help me to understand that at that particular point of time is the correct answer stored for the smaller subproblem or not. We'll check. If it is -1, that means I have not yet calculated the answer to that particular smaller subproblem. So what we'll do in that case, we'll go further. Like if you observe this recursion tree, for the very first time when we come over here, we are checking if this particular position DP22 is -1 or not. If it is not -1, we'll let our equation call go further. But once it comes to this point, again, let's say once it comes to this point, at this point of time, it will already have its answer stored in 2, 2. Hence, we could get rid of this part of the calculation. That's the power of dynamic programming. Okay, we could get rid of this part of the tree. All right. Now, one doubt which can come to your mind is how come this will be visited later, this will be visited first. Okay. So if we have studied traversals, then we are going to traverse this particular tree in a depth first fashion. Okay, let me just, yeah, in a depth first fashion. When I say depth first fashion, what do I mean to say? Like it will go from here to its entire depth until and unless it hits the base case. Then it will backtrack. It will go to this part. Okay. Then let me change the color. Yeah. Then the answer for smaller subproblems. Okay. Answer for this subproblem and this subproblem will be ready. It will be added and passed as an answer to this one. Okay. Then again it will backtrack. It will come here. Okay. It will see 3 comma 2, it will go down, okay, calculate the answer for this smaller sub problems. Obviously it will also go further down. I hope you get the feel what I'm trying to say, right? Like two smaller sub problems, answer will be calculated, it will be added and passed to its parent. So as you see, like I'm traversing a depth first fashion, so I first go from, like I'm traversing all the left part of the tree, then like I'm going from here to here, then I am again going to this node, and this node I'm not yet giving the answer for this node till now. I'll go to this part, I'll calculate this part of answer, I'll do the addition, and finally I return it. So that's the reason this 2 comma 2 will come later, this 2 comma 2. Okay, see, even if the things are not clear right now, it will make sense once I show you the code. Okay, because we will code it accordingly, so don't worry about it. And if you have any doubts, you can surely ask in the comment section. Okay, so I hope this much is enough. Okay, let's get back to the code now. Let me maximize it. Yeah. All right. So we are using mod over there. Let me read the question, because there was one part where you need to take care of mod. Okay. So these are small things that we need to take into consideration. Okay. Like we read the question. If we miss some part of the things, then even if your logic is correct, you have done 100% everything great, but still your answer will not match with the output of the given online portal. Okay. Yeah. So if you go down, yeah, it is saying over here that you don't need to read input or print anything. Complete the function number of paths, okay, which is this one, number of paths, which takes m and n as input, okay, parameters, and returns count of all the possible paths. This we already understood. The next line is the answer may be very large. Compute the answer modulo 10 to the power 9 plus 7. So they are saying that at the end, what you need to do, you need to take modulo of your final answer. Okay, that's great. So now let's have a look at the code. So initially, we have a long data type variable mod, which is initialized with 10 to the power 9 plus 7. I have taken a global DP array, okay, that is taken globally, and we were asked to complete this number of paths function. So let me just take the marker. Yeah, it's working. Great. So what we are doing over here, we have taken a nested for loop, and we are initializing our DP array with -1. Now you might ask a question, why have I taken from 1 comma 1? Why not 0 0? So if you go back to the video from the beginning of this lecture, we are talking in terms of indexing 1, right? If you remember, we are talking in terms of indexing of 1, right? Fine. So that's the reason we are initializing our DP array with 1 1. Now, how will the DP array look like for this 3 cross 3 grid? There will be 4 rows and 4 columns. Okay, to be more precise, there will be 4 rows and 4 columns. And with the help of this nested for loop, we are doing -1 at these positions. Okay, we are doing -1 at these positions. All right. Once after doing this, and you know, right, why we are doing -1, because this will keep a check for us, like we have calculated the answer for the smallest subproblem or not. Like for example, if I take this position, it will check whether dp 2 comma 3 is computed or not. If it is computed, we'll have some other answer than -1, right? Now I'll just like to add a smaller input, like which is not required in this question, but in some of the questions what you'll find is -1 is also a valid output. Okay, so there you need to understand that if you use -1, you won't be able to differentiate, right? You won't be able to differentiate between your answer and what you're trying to check. So at that point of time, you need to initialize it with something else. I hope you get the feel, right, what I'm trying to say. Over here I know that -1 could not be my possible answer, hence I'm keeping it as a check. Okay, fine, let's proceed forward. So after initialization, I'm calling solve mn and finally returning it. So now let's try to understand solve mn. So solve mn takes integer m, that is our rows, integer n, that is our columns. See, very initially, like as soon as I enter my function, I'm checking if it is not equal to -1, straight away return. I don't want to do extra work. Why will I do? If it is not equal to -1, that means I already have the answer for that part, right? So I'll straight away return. Else I've written the base case. Okay, we can modify this base case also, like you can again store like as I'm storing over here, right? You can also store over here like dp m comma n equals to 1 and return dp n comma n, but that's not required. Like, see, code should be clean and readable, right? So this is your base case, you're straight away returning 1. And I hope you remember the logic for this also, where we were taking smaller inputs like 1 column or 1 row. Okay, yeah. After this, what I have written? I have written a straight recursive formula that I have explained multiple times in my logic. So this is solve m comma n minus 1, solve m minus 1 comma n, finally taking the mod of them and If it is calculated, I am storing it in dpm comma n and returning it. See, I would suggest you that you yourself try to do a dry run of it, and if you have any problem, you can always ask in the comment section, because I've explained the similar thing while I was going through the logic. I have drawn the full recursive tree and I have showed like how we were calling and with the help of each cells in our grid, right? So I hope the code is making sense to you. And finally, we are returning dpm command. So if you know how recursion works, this will go to this part of the tree. Okay, then this will calculate all its left and right childs. It will return the answer with the summation to the root. And finally, if you look at this over here, we will do the summation of this part and this part, and we'll return it to over here. And at the end, you will be returning dp 3 comma 3, right? So there you will have your final answer, because dp 3 comma 3 was your first call, so it will end at the end, because this is how you're doing the dfs traversal. Like you're going to the left half, then both the childs returning the sum. This in this way you go up and up and up, then you again move to your right half, then you calculate both the left and right half answers to the sum and go up and up and up, and finally you return with the help of full left subtree answer, full right subtree answer, do the summation and return it. And wherever you find a similar sub problem, you are doing a very smart check. And this concept is called memoization. Okay. What you're doing, you have taken a extra space, but that extra space is helping you reduce your time complexity. So at the cost of space complexity, you are reducing your time complexity. Okay. So I hope this is clear to you. Now let's try to run this code. Yeah, let's first compile it. Yeah, so for 3, 3, you have your answer as 6. Now, if you see over here, okay, let me go to the top. For 3, 3, we had 6, okay. Let me submit it. Yeah, so there you go. You have your correct answer and the execution time is 0.01. So at the end, as I do in my every live lesson, I would just like to add one point that in these kind of questions, try to think in a more general manner. Okay, think in terms of smaller sub problems. Like, see, if I would have thought in the very beginning, like I need to count all the possible paths. I have these two choices that I can either go right or down. In an interview, I would have become nervous, right? So, what you need to do, you need to frame your answer in such a way that if it is working for n and m, it should also work for n minus 1 and m minus 1. So, the idea is to get a general approach and find out a base case where you will be ending, okay, or where you will come out of your infinite calls of the same function again and again, right? And in order to improvise, we have already seen that if we have same sub problems getting called again and again, then what we can do, we can use an extra space and store our previous answers. So in entire lecture of today, if you had any doubt, okay, or any part of the explanation, if you did not understand, okay, you can ask me in the comment section. I'll answer all of them. Okay. So yeah, this was it for today. This was asked recently in an interview at Adobe, and this was a good question. Okay, although the tag is easy, but if you're not good with recursion or the concept of memoization and dynamic programming, then even if your logic is correct, you might get TLE if you have not used extra space, or if you're writing the wrong recursive formula. If you're writing, then you might also get wrong answer. So just keep a note of all these things. Read your question full. Like if you remember, this modulo is playing a role, because if you don't do this, then also you might get your answer wrong even after you have done everything. Like even if you have taken a DP array, even if you have written the recursive solution formula in a very proper way, still you will get wrong answer if you don't read these things properly, right? So this is one thing which you need to observe. And what possible paths are allowed? Like in some of the questions, you're also allowed to move diagonally, right? So there you can do the modifications accordingly. So yeah, so I hope the code was clear to you. Now I can take some questions if there are any. All right. Thank you guys. Thank you for joining Geeks for Geeks practice. As I see that there are no questions, so we'll be coming up with good questions from various product based companies every week. Okay. Thank you for joining us.